Age reversal protocols have long fascinated humanity, with researchers, biohackers, and wellness enthusiasts constantly seeking ways to extend human longevity and reverse the effects of aging. The recent case of a man who reportedly became 10 years younger by following entrepreneur Bryan Johnson's age reversal plan has sparked intense debate regarding the feasibility, ethics, and implications of such regimens. Bryan Johnson, a tech entrepreneur turned longevity enthusiast, has been at the forefront of radical anti-aging experimentation, investing millions in reversing his biological age. His protocols, heavily science-backed and meticulously monitored, involve extreme dietary restrictions, rigorous exercise routines, advanced supplementation, and medical interventions aimed at cellular rejuvenation. The case of an individual successfully achieving a decade-long reversal in biological aging has intrigued both the scientific community and the general public, raising questions about the effectiveness, practicality, and long-term viability of such programs. The foundation of Bryan Johnson's approach lies in extensive biomarker tracking, where every aspect of his body's aging process is quantified and analyzed. This includes epigenetic clocks, blood biomarkers, organ health assessments, and body composition scans. Johnson's personal project, known as Project Blueprint, serves as a template for those seeking extreme age reversal. The methodology is centered around reducing inflammation, optimizing mitochondrial function, enhancing cellular repair mechanisms, and mitigating oxidative stress, all of which contribute significantly to the aging process. The man who reportedly reversed his biological age by 10 years adhered to a strict version of this plan, following a highly regimented lifestyle that included dietary changes, intensive physical activity, regular medical monitoring, and experimental anti-aging treatments. One of the key components of this age reversal plan is a meticulously designed diet that prioritizes nutrient density while eliminating factors that accelerate aging. The diet follows a strict caloric intake, focusing on plant-based whole foods rich in antioxidants, polyphenols, and essential fatty acids. The elimination of processed foods, refined sugars, and inflammatory ingredients helps reduce systemic inflammation, which is a major contributor to aging-related diseases. Intermittent fasting and time-restricted eating play a crucial role in the protocol, promoting autophagy, a cellular repair process that clears out damaged cells and enhances longevity. Additionally, protein intake is carefully monitored to balance muscle preservation while avoiding excessive activation of growth pathways such as mTOR and IGF-1, which are linked to accelerated aging. Exercise is another fundamental pillar of the program, designed to optimize cardiovascular health, muscle mass, and metabolic efficiency. High-intensity interval training, HIIT resistance training, and endurance exercises are incorporated to improve mitochondrial function and stimulate the production of key longevity-related hormones such as growth hormone and testosterone. The man who successfully reversed his biological age followed an aggressive workout regimen, ensuring a balance between strength training, flexibility exercises, and cardiovascular conditioning. Regular movement throughout the day, rather than prolonged periods of inactivity, is emphasized to prevent metabolic slowdown and maintain optimal physiological function. Supplementation forms a crucial aspect of the age reversal strategy, with a wide range of compounds aimed at targeting cellular pathways associated with aging. NAD+ boosters, such as nicotinamide riboside (NR) and nicotinamide mononucleotide (NMN), play a pivotal role in enhancing mitochondrial health and cellular energy production. Antioxidants like resveratrol, quercetin, and glutathione are included to combat oxidative stress and reduce DNA damage. Adaptogenic herbs, omega-3 fatty acids, and specific amino acids are also integrated to support cognitive function, cardiovascular health, and muscle recovery. The precision of supplementation is based on personalized biomarker analysis, ensuring that deficiencies and imbalances are corrected in real time to optimize physiological function. Sleep optimization is another critical element in the protocol, recognizing the profound impact of sleep on aging and overall well-being. The individual who achieved a decade-long biological age reversal adhered to a strict sleep routine, prioritizing deep, restorative sleep cycles. Factors such as blue light exposure, circadian rhythm alignment, and bedroom environment optimization were meticulously managed. Melatonin supplementation, magnesium, and relaxation techniques such as meditation and breathwork were incorporated to enhance sleep quality, thereby promoting cellular repair and reducing stress-related aging markers. Medical interventions and biohacking techniques played a significant role in accelerating the age reversal process. Hormone optimization, including testosterone replacement therapy (TRT) and growth hormone secretagogues, was carefully monitored to maintain youthful levels of vital hormones while minimizing associated risks. Peptide therapies, such as BPC-157 and thymosin beta-4, were used for tissue repair and inflammation reduction. Stem cell treatments and exosome therapy were explored to rejuvenate aging tissues and promote regeneration at the cellular level. Regular blood transfusions, hyperbaric oxygen therapy, and cryotherapy sessions were employed to enhance circulation, reduce oxidative stress, and stimulate longevity-related pathways. Despite the remarkable results achieved, the approach is not without controversy. Critics argue that such extreme interventions may pose long-term risks, including unknown side effects of experimental treatments and the ethical considerations surrounding access to these advanced protocols. The financial burden associated with such a regimen is substantial, making it an option available only to the elite few who can afford constant medical supervision, specialized treatments, and cutting-edge technologies. Additionally, the psychological impact of adhering to such a highly regimented lifestyle raises concerns about sustainability and quality of life. The strict limitations on diet, social interactions, and lifestyle choices may lead to mental stress and decreased enjoyment of life, counteracting some of the perceived benefits. Another critical concern revolves around the scientific validity of age reversal claims. While the individual in question demonstrated a 10-year reduction in biological markers of aging, the long-term efficacy and reproducibility of such results remain uncertain. Aging is a multifaceted process influenced by genetic, environmental, and lifestyle factors, and the ability to consistently reverse biological age across diverse populations has yet to be proven conclusively. Moreover, ethical concerns arise regarding the pursuit of age reversal, with questions about whether extending lifespan should take precedence over improving the quality of life in later years. Nevertheless, the implications of successful age reversal protocols could be revolutionary for the future of healthcare and longevity science. If refined and made more accessible, these interventions could potentially extend healthy lifespan, reduce the burden of age-related diseases, and transform the way society approaches aging. Medical advancements in regenerative medicine, gene therapy, and cellular rejuvenation continue to push the boundaries of what is possible, paving the way for a future where aging is no longer an inevitable decline but a process that can be actively managed and even reversed. The case of the individual who reversed 10 years of aging through Bryan Johnson's protocol serves as a testament to the power of disciplined lifestyle modifications, cutting-edge science, and biohacking techniques. While the journey towards age reversal is still in its early stages, the potential benefits and risks of such interventions continue to fuel debates within the scientific and medical communities. As research advances and more data becomes available, the future of age reversal may transition from an experimental endeavor to an integrated part of preventive medicine, offering hope for those seeking to extend both their lifespan and health span. The ongoing discourse surrounding age reversal protocols is deeply rooted in the intersection of biotechnology, personalized medicine, and lifestyle interventions. While Bryan Johnson's extreme approach to longevity has sparked enthusiasm, it has also raised critical questions about the broader implications of attempting to reverse biological aging. The man who reportedly became 10 years younger by following this regimen exemplifies both the promise and the limitations of such interventions. One of the most striking aspects of this protocol is the degree of precision involved. Unlike generic health and wellness programs, which provide broad guidelines, Johnson's age reversal plan operates on a granular level. Every aspect of physiology is meticulously measured, from hormone levels to mitochondrial efficiency, allowing for real-time adjustments to diet, supplementation, exercise, and medical interventions. This hyper-personalized approach is made possible through advancements in biotechnology, where comprehensive blood tests, genetic analysis, and continuous biomonitoring provide unparalleled insight into an individual's biological state. The ability to fine-tune interventions based on empirical data is what sets this protocol apart from conventional longevity strategies. The importance of cellular health in aging cannot be overstated. One of the primary objectives of age reversal protocols is to mitigate cellular senescence, a state in which cells lose their ability to divide and function effectively. Senescent cells contribute to inflammation and tissue degeneration, accelerating the aging process. Bryan Johnson's regimen incorporates senolytics, compounds designed to selectively eliminate senescent cells, to promote cellular rejuvenation. Substances such as fisetin, quercetin, and dasatinib have shown promise in preclinical studies for their ability to clear out dysfunctional cells and enhance tissue repair. The individual who achieved a decade-long biological age reversal reportedly included these compounds in his supplementation routine, highlighting their potential role in slowing down the aging process. Mitochondrial health is another cornerstone of this protocol. Mitochondria, often referred to as the powerhouses of the cell, play a crucial role in energy production and metabolic regulation. As individuals age, mitochondrial function declines, leading to decreased energy levels and increased oxidative stress. The age reversal protocol places significant emphasis on mitochondrial optimization through a combination of dietary strategies, exercise, and targeted supplementation. Compounds such as coenzyme Q10, CoQ10, pyrroloquinoline PQQ, and alpha-lipoic acid ALA are included to support mitochondrial efficiency and reduce oxidative damage. Additionally, aerobic exercise and interval training stimulate mitochondrial biogenesis, encouraging the production of new, healthy mitochondria to sustain cellular energy demands. One of the more controversial aspects of the protocol is the use of experimental therapies such as stem cell infusions and plasma exchange. Stem cell therapy has gained attention for its potential to regenerate damaged tissues, reduce inflammation, and enhance organ function. The idea behind this approach is that introducing young, healthy stem cells into an aging body could rejuvenate various physiological systems. While early studies suggest potential benefits, the long-term safety and efficacy of stem cell treatments remain under investigation. Similarly, plasma exchange, where older individuals receive plasma from younger donors, has been explored as a method to rejuvenate the circulatory system and improve cognitive function. Although animal studies have shown promising results, human trials are still in their infancy, and ethical concerns regarding plasma donation and accessibility persist. Another fundamental aspect of the age reversal strategy is metabolic flexibility. The ability to efficiently switch between fuel sources, such as glucose and fat, plays a critical role in longevity. The protocol emphasizes intermittent fasting, ketogenic cycling, and caloric restriction as methods to improve insulin sensitivity and enhance metabolic resilience. Fasting has been shown to activate autophagy, a process that clears out damaged proteins and cellular debris, promoting longevity at the cellular level. The individual who successfully reversed his biological age followed a strict fasting protocol, incorporating both intermittent fasting and periodic extended fasts to optimize metabolic function and cellular repair. Beyond the physiological components, mental health and stress management play an essential role in the protocol. Chronic stress accelerates aging by increasing cortisol levels, which contribute to inflammation and cellular damage. Meditation, breathwork, and mindfulness practices are integrated into the regimen to promote relaxation and enhance cognitive longevity. Additionally, neuroplasticity-enhancing interventions, such as learning new skills, engaging in creative activities, and using nootropic supplements, support brain health and cognitive function. The emphasis on mental well-being underscores the holistic nature of the protocol, recognizing that longevity is not merely about extending lifespan but also about maintaining a high quality of life. Critics of extreme age reversal protocols argue that the pursuit of longevity should not come at the expense of living a fulfilling and balanced life. The strict adherence required for such regimens can be mentally and socially isolating, raising questions about whether the trade-offs are worth the potential benefits. Furthermore, concerns about accessibility and equity remain a significant issue. The level of medical monitoring, specialized treatments, and biohacking technologies involved in this protocol are cost-prohibitive for the average person, creating a divide between those who can afford longevity interventions and those who cannot. This raises ethical questions about whether advancements in age reversal will ultimately widen health disparities rather than democratize access to healthier aging. Despite these challenges, the field of longevity science continues to advance at a rapid pace. Researchers are exploring novel interventions such as gene therapy, epigenetic reprogramming, and artificial intelligence-driven health optimization to push the boundaries of what is possible. Companies specializing in longevity biotechnology are investing heavily in developing pharmaceutical solutions that could mimic the effects of caloric restriction, enhance cellular repair, and slow down aging at the molecular level. As scientific understanding deepens, the hope is that more accessible and scalable solutions will emerge, allowing a broader population to benefit from advancements in age reversal science. The case of the man who successfully reversed 10 years of biological aging through Bryan Johnson's protocol represents a glimpse into the future of personalized longevity interventions. While the results are promising, they also underscore the complexity of aging and the multifaceted nature of human health. Whether such extreme measures will become mainstream or remain within the domain of elite biohackers remains to be seen. However, one thing is certain: the pursuit of longevity is no longer confined to science fiction but is rapidly becoming a tangible reality, challenging long-held assumptions about what it means to grow old. As the discussion on age reversal protocols continues, it is essential to examine the scientific mechanisms underlying these interventions and their potential implications for the future of healthcare. The ability to reverse biological age by 10 years, as demonstrated by the individual following Bryan Johnson's regimen, suggests that targeted interventions can significantly impact cellular aging. However, the long-term sustainability, risks, and ethical concerns of such regimens remain at the forefront of the conversation. One of the primary scientific foundations of age reversal protocols lies in epigenetic reprogramming. Epigenetics refers to changes in gene expression that occur without altering the underlying DNA sequence. Over time, environmental factors such as diet, stress, and toxins can lead to unfavorable epigenetic modifications that accelerate aging. Bryan Johnson's protocol incorporates interventions designed to reset these epigenetic markers, effectively restoring youthful gene expression patterns. This approach includes lifestyle factors such as fasting, specific nutrient intake, and pharmacological compounds that influence epigenetic regulators like sirtuins, AMPK, and mTOR. Sirtuins, a family of proteins known for their role in longevity, play a crucial role in cellular health. These proteins are involved in DNA repair, inflammation reduction, and mitochondrial function. Activating sirtuins through compounds such as resveratrol and nicotinamide adenine dinucleotide (NAD+ boosters is a key component of Johnson's approach. NAD+ levels decline with age, leading to reduced cellular energy production and increased oxidative stress. By supplementing with precursors like NMN or NR, individuals can potentially restore youthful NAD+ levels, enhancing their body's ability to repair damaged cells and maintain metabolic efficiency. Another critical aspect of age reversal is telomere length maintenance. Telomeres, the protective caps at the ends of chromosomes, shorten with each cell division, contributing to cellular aging. Shortened telomeres are associated with increased disease risk and reduced lifespan. Strategies to slow telomere shortening or even extend telomere length are being explored as potential longevity interventions. Johnson's protocol likely includes compounds such as TA65, a telomerase activator, and lifestyle practices that minimize oxidative stress and inflammation, both of which accelerate telomere attrition. Autophagy, the body's natural mechanism for clearing out damaged cells and proteins, is another crucial factor in the aging process. Fasting and calorie restriction have been shown to activate autophagy, promoting cellular repair and longevity. The individual who successfully reversed his biological age followed strict fasting regimens, which likely enhanced autophagic processes. Additionally, compounds like spermidine, found in certain foods and supplements, have been identified as autophagy inducers, further supporting cellular rejuvenation. The role of inflammation in aging cannot be overstated. Chronic low-grade inflammation, often referred to as inflammaging, contributes to many age-related diseases, including cardiovascular conditions, neurodegenerative disorders, and metabolic dysfunction. The age reversal protocol prioritizes an anti-inflammatory lifestyle, incorporating omega-3 fatty acids, polyphenols, and other bioactive compounds known for their ability to modulate inflammatory pathways. Moreover, regular exercise, particularly resistance training and cardiovascular workouts, has been shown to reduce systemic inflammation and support healthy aging. One of the more controversial components of the protocol involves hormone optimization. As individuals age, levels of key hormones such as testosterone, growth hormone, and DHEA decline, leading to reduced muscle mass, slower metabolism, and decreased cognitive function. Johnson's regimen includes precise hormone monitoring and, in some cases, hormone replacement therapy (HRT) to restore youthful levels. While this approach can have significant benefits, it also carries risks, including potential cardiovascular complications and increased cancer susceptibility. The debate over the safety and ethics of hormone optimization in longevity science remains ongoing. Beyond the physiological aspects, psychological well-being is a fundamental part of the age reversal strategy. Stress, anxiety, and depression can accelerate aging at the cellular level, primarily through increased cortisol levels and inflammatory responses. The protocol emphasizes meditation, mindfulness, and social engagement as crucial factors in maintaining mental resilience. The individual who reversed 10 years of biological age likely incorporated stress reduction techniques such as deep breathing exercises, cognitive behavioral therapy (CBT), and biofeedback training to enhance overall well-being. The role of sleep in aging reversal is also critical. Sleep deprivation has been linked to increased oxidative stress, impaired cognitive function, and hormonal imbalances that contribute to accelerated aging. The protocol follows strict sleep hygiene practices, ensuring that the body undergoes sufficient deep and REM sleep cycles. Blue light exposure is minimized, and melatonin supplementation is used strategically to support circadian rhythm alignment. Emerging technologies such as smart mattresses and wearable sleep trackers further enhance sleep optimization by providing real-time feedback on sleep quality. Another innovative aspect of Johnson's approach involves the use of artificial intelligence and data analytics to fine-tune health interventions. Continuous monitoring of physiological markers allows for personalized adjustments in diet, exercise, and supplementation, ensuring that the protocol remains adaptive to an individual's changing needs. AI-driven insights can predict potential health risks, enabling proactive intervention before the onset of age-related conditions. This data-driven approach represents a significant shift in the way longevity science is being implemented, moving from a one-size-fits-all model to a highly customized strategy. Despite the promising results, there are significant challenges and ethical dilemmas associated with extreme longevity interventions. One major concern is accessibility. The costs associated with comprehensive biomarker testing, cutting-edge medical treatments, and continuous monitoring make these protocols unattainable for the average person. This raises questions about whether longevity advancements will create a new form of inequality, where only the wealthy can afford to extend their lifespan and maintain peak health. Another ethical concern revolves around the societal implications of extending human life. If age reversal technologies become widely available, there could be profound effects on population dynamics, resource distribution, and economic systems. The potential for increased lifespan without corresponding improvements in quality of life could lead to unintended consequences, such as prolonged periods of frailty and increased healthcare burdens. Policymakers and bioethicists must address these issues to ensure that longevity science benefits society as a whole. There is also the question of whether extreme longevity interventions align with human nature and the concept of aging as a natural process. Some critics argue that attempting to reverse aging to such an extent disrupts the natural life cycle and raises philosophical questions about the meaning of life and mortality. While scientific advancements can enhance quality of life and health span, the pursuit of indefinite life extension may lead to unforeseen consequences that challenge our understanding of human existence. Ultimately, the case of the man who reversed 10 years of biological aging serves as a fascinating example of what is possible when science, technology, and discipline converge in the pursuit of longevity. His success highlights the potential for targeted interventions to slow down or even partially reverse aging, offering hope for future breakthroughs in regenerative medicine. However, it also underscores the complexities and uncertainties associated with pushing the boundaries of human biology. As research continues to evolve, the field of longevity science is likely to uncover new insights that refine and improve age reversal strategies. While extreme protocols like Bryan Johnson's may remain inaccessible to most people, the principles behind them, such as optimizing nutrition, exercise, sleep, and stress management, can be adopted at various levels to promote healthier aging. The key challenge moving forward will be to develop scalable, evidence-based solutions that make age reversal benefits available to a broader population while addressing the ethical and societal implications of extended lifespans. The pursuit of longevity is no longer a speculative endeavor confined to science fiction. It is an active field of research and experimentation, with the potential to redefine human health and lifespan in the coming decades. Whether the dream of reversing aging becomes a widespread reality remains to be seen, but one thing is certain: the conversation around longevity science is only just beginning. As the field of longevity science progresses, it is essential to consider the broader implications of age reversal protocols beyond individual success stories. The case of the man who reportedly reversed 10 years of biological aging by following Bryan Johnson's regimen is a remarkable testament to the potential of these interventions. However, the sustainability, scalability, and long-term effects of such protocols remain key areas of debate. One of the most pressing questions surrounding age reversal is the reproducibility of results. While biomarkers such as epigenetic clocks, telomere length, and mitochondrial efficiency can provide quantifiable measures of biological age, aging is a complex and multifaceted process influenced by genetic, environmental, and lifestyle factors. The extent to which a highly regimented protocol can produce consistent age reversal effects across different individuals is still unclear. Variability in genetic predisposition, metabolic rates, and baseline health conditions means that not everyone may experience the same degree of biological age reduction, even when following identical interventions. The role of genetic predisposition in longevity is a critical consideration. Some individuals naturally age more slowly due to favorable genetic factors that influence cellular repair mechanisms, immune function, and resistance to oxidative stress. While lifestyle modifications can significantly impact aging, the extent to which they can override genetic predispositions remains an open question. The individual who successfully reversed 10 years of aging may have had genetic advantages that contributed to his response to the protocol, raising questions about whether such results are achievable for the broader population. Another factor influencing the effectiveness of age reversal protocols is adherence. The strict dietary, exercise, and lifestyle requirements of Bryan Johnson's regimen demand an exceptional level of discipline and consistency. While some individuals may be willing to commit to such an intensive routine, the vast majority of people struggle with long-term adherence to even basic health guidelines. Sustainability is a significant challenge in longevity science, as interventions must be practical and accessible to be widely adopted. The question then becomes whether simplified or modified versions of these protocols can still yield meaningful benefits without requiring extreme lifestyle changes. The psychological and social aspects of extreme longevity interventions also warrant consideration. While extending lifespan and improving health span are desirable goals, the impact of rigid lifestyle constraints on mental well-being and social relationships cannot be ignored. The individual who reversed his biological age likely had to make significant sacrifices in terms of food choices, social interactions, and leisure activities to adhere to the protocol. The psychological burden of constantly monitoring biomarkers, optimizing every aspect of health, and maintaining an intense regimen may lead to stress and anxiety, counteracting some of the benefits of longevity interventions. Finding a balance between optimizing health and maintaining a fulfilling life is crucial in the pursuit of age reversal. From a technological perspective, advancements in AI-driven health optimization and precision medicine are expected to play an increasingly significant role in refining age reversal strategies. AI-powered diagnostics, continuous health tracking, and personalized intervention algorithms have the potential to make longevity science more accessible and efficient. Real-time data analysis can provide insights into individual responses to interventions, allowing for dynamic adjustments to optimize health outcomes. The integration of machine learning with longevity research could lead to the development of adaptive protocols that adjust to an individual's unique biological needs over time. Regenerative medicine is another promising frontier in age reversal research. Stem cell therapy, tissue engineering, and organ regeneration hold the potential to repair and replace aging cells and tissues, offering a more comprehensive approach to reversing the aging process. While current stem cell treatments are still in the experimental stage, ongoing research aims to develop more effective and widely available therapies. If successful, these advancements could complement lifestyle-based longevity interventions, providing a more holistic strategy for age reversal. The ethical implications of age reversal protocols continue to generate debate. One of the primary concerns is the potential societal impact of significantly extending human lifespan. If people begin living much longer, the economic and social structures of society may need to adapt to accommodate an aging but active population. Workforce dynamics, retirement policies, and healthcare systems may require restructuring to support individuals who maintain high levels of productivity and functionality well into old age. Additionally, questions about overpopulation, resource distribution, and environmental sustainability must be addressed to ensure that longevity advancements do not create unforeseen global challenges. Another ethical consideration is the disparity in access to age reversal technologies. As with many cutting-edge medical advancements, the initial implementation of these protocols is likely to be limited to those who can afford expensive treatments, continuous health monitoring, and personalized medical interventions. This raises concerns about whether longevity science will exacerbate existing health inequalities, creating a divide between those who have access to life-extending technologies and those who do not. Efforts to democratize longevity research and make age reversal interventions more widely available will be crucial in addressing these concerns. The philosophical implications of reversing aging also warrant exploration. Aging has historically been viewed as an inevitable part of the human experience, shaping cultural attitudes toward life, death, and legacy. The potential to extend lifespan and maintain youthfulness challenges long-standing beliefs about the natural progression of life. Some argue that embracing aging as a natural process is essential for personal growth and societal renewal, while others see the pursuit of longevity as a logical extension of medical progress. These differing perspectives highlight the need for ongoing ethical discussions about the role of age reversal science in shaping the future of humanity. Despite these challenges, the momentum behind longevity research continues to grow. Governments, research institutions, and biotech companies are investing heavily in age reversal science, recognizing its potential to revolutionize healthcare and improve quality of life. Clinical trials exploring novel anti-aging therapies, including senolytics, gene editing, and metabolic interventions, are underway, bringing us closer to a future where age-related decline may no longer be inevitable. In the broader context, the case of the man who reversed 10 years of biological aging serves as a powerful demonstration of what is possible when science, discipline, and technology converge. While his success raises questions about feasibility and accessibility, it also provides valuable insights into the mechanisms of aging and how they can be manipulated. As research progresses, the ultimate goal will be to translate these findings into practical, scalable solutions that benefit a larger population without requiring extreme measures. The field of longevity science is at a pivotal moment, where scientific breakthroughs are challenging traditional notions of aging and mortality. Whether extreme age reversal protocols will become widely adopted or remain niche interventions for a select few remains uncertain. However, the ongoing exploration of anti-aging strategies continues to push the boundaries of human health and potential, paving the way for a future where longer, healthier lives may be within reach for all. As longevity science continues to evolve, the broader implications of age reversal protocols extend beyond individual success stories to potential shifts in public health, economics, and human psychology. The case of the man who reportedly reversed 10 years of biological aging following Bryan Johnson's regimen serves as an intriguing benchmark for what may be possible with precise interventions. However, to determine whether such outcomes can be replicated and sustained, researchers must further explore the mechanisms of aging and their modulation through lifestyle, biotechnology, and medicine. One of the fundamental questions in age reversal science is whether biological age reversal translates into increased lifespan or merely improves health in the short term. While biomarkers indicate that this individual achieved a decade-long reduction in biological age, the long-term impact on his overall lifespan remains unknown. Reversing specific aging markers, such as epigenetic age, telomere length, and mitochondrial function, does not necessarily mean that overall mortality risk is significantly reduced. Longevity scientists must continue to investigate whether these interventions merely delay the visible signs of aging or if they genuinely extend human lifespan. Another important consideration is the distinction between health span and lifespan. Health span refers to the number of years an individual remains free of age-related diseases, while lifespan is the total number of years lived. The primary goal of most longevity interventions, including Bryan Johnson's protocol, is to extend health span, ensuring that individuals remain physically and cognitively functional for as long as possible. While improving biological markers may reduce the risk of chronic illnesses, questions remain about whether it can extend absolute lifespan beyond natural limits. The impact of age reversal protocols on disease prevention is particularly promising. Many age-related conditions, including cardiovascular disease, neurodegenerative disorders, and metabolic syndromes, are closely linked to cellular aging mechanisms. By targeting inflammation, oxidative stress, and mitochondrial dysfunction, longevity interventions may reduce the incidence of these conditions, potentially decreasing overall healthcare costs and reducing the burden on medical systems. If more individuals remain healthy into their later years, the shift from treating age-related diseases to preventing them could transform the structure of healthcare as we know it. However, concerns arise regarding the potential unintended consequences of extreme longevity interventions. If large portions of the population begin living significantly longer, the strain on social systems such as pension plans, retirement funds, and workforce structures could be substantial. The economic implications of an aging but active population would require significant adjustments in labor policies, social security systems, and healthcare infrastructure. Governments and policymakers must anticipate these changes and plan for a future where extended health spans become more common. A related issue is the question of overpopulation. If individuals routinely live decades longer than they do today, the global population could expand at an unprecedented rate, leading to increased competition for resources such as food, water, energy, and housing. While some argue that technological advancements in sustainability and resource management will mitigate these challenges, others warn that extending human lifespan without addressing broader environmental and economic concerns could create unintended global crises. Beyond the economic and demographic impacts, the psychological effects of prolonged lifespan are another critical area of study. If individuals are no longer bound by the traditional constraints of aging, how will that affect their motivation, purpose, and decision-making? Historically, the finite nature of life has influenced human behavior, encouraging people to pursue careers, start families, and strive for achievements within a limited time frame. If aging becomes significantly delayed, societal norms surrounding career progression, relationships, and personal development may shift dramatically. People may take more time to explore multiple careers, delay major life decisions, or even reconsider traditional notions of legacy and mortality. Another psychological aspect to consider is the potential for longevity fatigue. Some researchers speculate that, if people live much longer, they may experience existential or emotional exhaustion, questioning the meaning of life when mortality is no longer an immediate concern. The possibility of extended lifespans raises philosophical questions about the human experience, including whether life's value is inherently tied to its impermanence. While some individuals may embrace the idea of extended youthfulness and vitality, others may struggle with the concept of living for an exceptionally long time. Despite these uncertainties, research into longevity and age reversal continues to gain traction. Several emerging technologies and scientific advancements could further enhance the effectiveness of age reversal strategies. These include 1. Gene editing and epigenetic reprogramming. Scientists are exploring CRISPR-based gene editing techniques to repair DNA damage associated with aging. Additionally, epigenetic reprogramming, pioneered by researchers like Dr. David Sinclair, aims to reset cells to a more youthful state using factors that reverse cellular aging. 2. Senolytic therapies. These drugs target and eliminate senescent, aging cells that contribute to inflammation and tissue degeneration. By selectively clearing these cells, senolytics have the potential to improve organ function and reduce age-related diseases. 3. Artificial intelligence in longevity science. AI-driven health optimization platforms are being developed to provide real-time feedback on biological aging, offering personalized recommendations based on continuous health data. 4. Organ regeneration and tissue engineering. Advances in regenerative medicine, including lab-grown organs and stem cell-based tissue repair, could provide replacement options for aging tissues, potentially extending lifespan without the limitations of current medical treatments. 5. Metformin and rapamycin trials. These widely studied compounds show promise in extending lifespan by targeting cellular pathways linked to aging. Clinical trials are underway to determine their long-term safety and efficacy in humans. As these technologies progress, they may make age reversal strategies more accessible to the general population. Currently, extreme longevity protocols, such as those followed by Bryan Johnson, require significant financial investment and medical supervision. However, if scientific advancements lead to cost-effective interventions, longevity science could transition from being a luxury for the wealthy to a mainstream component of preventive healthcare. One of the most critical challenges moving forward is the need for robust, long-term studies to validate the efficacy of age reversal interventions. While preliminary results from self-experimenters and small-scale trials are promising, large-scale clinical trials are necessary to establish safety, effectiveness, and reproducibility. The longevity field must move beyond anecdotal success stories and focus on rigorous scientific validation to ensure that interventions are both beneficial and safe. In conclusion, the case of the man who reversed 10 years of biological aging serves as a fascinating glimpse into the potential of longevity science. His experience underscores the power of targeted interventions in modulating the aging process but also raises critical questions about feasibility, accessibility, and long-term outcomes. As research progresses, the goal will be to develop scalable, evidence-based longevity solutions that can be widely implemented without extreme lifestyle modifications. While the dream of reversing aging is no longer confined to science fiction, it remains a work in progress. The future of longevity science holds immense promise, but it also requires careful consideration of ethical, social, and economic factors. Whether society will embrace age reversal technologies or grapple with the consequences of extended lifespans remains to be seen. However, one thing is clear: the pursuit of longevity is shaping up to be one of the most transformative scientific endeavors of the 21st century. As longevity research continues to advance, the broader implications of age reversal science extend beyond individual cases like the man who reportedly became 10 years younger following Bryan Johnson's protocol. While his experience demonstrates the potential effectiveness of targeted interventions, it also raises critical questions about the biological, societal, and philosophical aspects of extending human life. The pursuit of longevity is not merely about reversing biological age but also about redefining the way we approach health, aging, and the very nature of human existence. One of the most intriguing aspects of age reversal protocols is their reliance on emerging scientific discoveries in fields such as cellular biology, regenerative medicine, and biotechnology. At the core of these interventions is the concept of cellular reprogramming, which aims to restore cells to a more youthful state. This process is inspired by Nobel Prize-winning research on induced pluripotent stem cells (iPSCs), which demonstrated that mature cells could be reprogrammed back into an embryonic-like state. Scientists are now exploring ways to apply similar techniques to slow or even reverse aging in human tissues. By using transient expression of Yamanaka factors, genes involved in cellular reprogramming, researchers hope to reset cells without causing uncontrolled growth or cancerous mutations. Another critical area of study in longevity science is the role of metabolic optimization in aging. The efficiency of cellular metabolism declines with age, leading to increased oxidative stress, mitochondrial dysfunction, and insulin resistance. Many age reversal protocols focus on metabolic interventions such as ketogenic diets, fasting, and caloric restriction, all of which have been shown to enhance longevity in animal models. These dietary strategies activate key longevity pathways, including AMP-activated protein kinase AMPK, the mammalian target of rapamycin mTOR, and sirtuins, all of which regulate energy metabolism and cellular repair processes. In addition to dietary modifications, pharmacological interventions play a growing role in longevity science. Some of the most promising anti-aging compounds being studied include rapamycin. Originally developed as an immunosuppressant, rapamycin has been shown to extend lifespan in multiple animal models by inhibiting mTOR, a pathway involved in cellular growth and aging. Some biohackers and longevity researchers have begun self-experimenting with low doses of rapamycin, though clinical trials in humans are still ongoing. Metformin, a widely used diabetes drug, metformin has been linked to increased lifespan in animal studies and improved health span in diabetic patients. It is believed to work by improving insulin sensitivity and activating AMPK, a key regulator of cellular energy balance. NAD+ boosters NR and NMN, nicotinamide riboside NR, and nicotinamide mononucleotide NMN, are precursors to NAD+, a molecule essential for energy metabolism and DNA repair. NAD+ levels decline with age, and supplementation has been proposed as a method to restore youthful cellular function. Senolytics, these are compounds that selectively target and eliminate senescent cells, which accumulate with age and contribute to inflammation and tissue dysfunction. Early trials suggest that clearing senescent cells may improve overall health and extend lifespan. While these interventions hold promise, they also raise important ethical and regulatory concerns. Many of the substances used in longevity research are either off-label applications of existing drugs or experimental compounds with limited human data. The long-term safety and potential side effects of these treatments remain uncertain, and regulatory agencies such as the FDA have yet to approve most of them for anti-aging purposes. This creates a complex landscape where some individuals are willing to experiment with longevity protocols despite the risks, while mainstream medicine remains cautious. Beyond pharmacology, technological advancements are playing an increasingly significant role in longevity science. AI-driven health monitoring systems, wearable devices, and continuous glucose monitors allow individuals to track biological markers in real time, providing a more personalized approach to longevity optimization. Companies like Bryan Johnson's Blueprint use real-time data analytics to adjust diet, supplementation, and exercise routines based on individual health metrics. This represents a shift toward precision medicine, where treatments and interventions are tailored to the unique biological profile of each individual rather than following a one-size-fits-all approach. However, one of the biggest challenges facing longevity science is the issue of accessibility. Currently, many of the most advanced age reversal protocols require significant financial investment, specialized medical supervision, and access to cutting-edge technologies. This raises concerns about whether longevity interventions will become another area of medical inequality, accessible only to the wealthy while remaining out of reach for the majority of the population. Efforts to democratize longevity science, such as making biomarkers testing more affordable, developing cost-effective treatments, and expanding public health initiatives focused on longevity, will be essential in ensuring that these advancements benefit society as a whole. Another major consideration in the longevity debate is the potential impact on population dynamics and global resources. If humans begin living significantly longer, how will this affect economic structures, social security systems, and the balance between working and retired populations? The traditional model of a career followed by retirement may no longer be sustainable if individuals remain healthy and productive well into their 80s, 90s, or beyond. This could lead to shifts in how societies structure education, employment, and family dynamics. For example, people may pursue multiple careers over their lifetime, delay having children, or reconsider traditional retirement ages. Philosophically, the pursuit of extreme longevity raises questions about the meaning and purpose of human life. Throughout history, mortality has been a defining aspect of the human experience, shaping cultural traditions, religious beliefs, and personal motivations. If aging becomes a largely manageable condition rather than an inevitable decline, how will that alter our perception of life's milestones? Some argue that extending lifespan could lead to greater fulfillment, allowing individuals more time to contribute to society, explore personal interests, and build deeper relationships. Others worry that it could result in stagnation, where people lose their sense of urgency and purpose. Despite these uncertainties, the pursuit of longevity science is accelerating at an unprecedented pace. Governments, private investors, and research institutions are pouring billions of dollars into aging research, with some experts predicting that significant breakthroughs could emerge within the next few decades. Whether through genetic engineering, regenerative medicine, or advanced AI-driven health optimization, the potential to slow or reverse aging is no longer a speculative concept but a field actively being developed. As research progresses, the conversation around longevity science will need to expand beyond the scientific community to include policymakers, ethicists, and the general public. Issues such as the regulation of anti-aging drugs, the economic implications of extended lifespans, and the ethical considerations of radically altering human aging will need to be addressed in a way that balances scientific progress with societal well-being. In conclusion, the story of the man who reversed 10 years of biological aging using Bryan Johnson's protocol is a compelling example of what may be possible in the future of longevity science. However, his case also highlights the complexities and challenges that come with attempting to extend human lifespan. While the biological mechanisms behind aging are becoming increasingly well understood, translating this knowledge into practical, widely accessible, and ethically sound interventions remains a significant challenge. As we move closer to a future where aging may no longer be an unchangeable reality, it is crucial to consider not just the scientific possibilities but also the broader impact on humanity as a whole. The pursuit of age reversal and longevity science is entering a transformative era, driven by cutting-edge research in genetics, biotechnology, and personalized medicine. While the case of the man who reportedly became 10 years biologically younger by following Bryan Johnson's protocol has captivated public interest, it is only a small glimpse into the larger movement reshaping our understanding of aging. The implications of extending human health span and potentially lifespan extend far beyond individual cases, influencing fields such as healthcare, economics, ethics, and even human identity. At the core of the age reversal movement is the growing understanding that aging is not an unavoidable fate but rather a biological process governed by molecular mechanisms that can be manipulated. Unlike the traditional view that considers aging as a random, inevitable deterioration, longevity scientists now see it as a programmed decline driven by genetic and environmental factors. Research into cellular senescence, mitochondrial function, and epigenetics has uncovered key pathways that regulate aging, many of which are now being targeted by longevity interventions. One of the most promising approaches to reversing biological aging is the concept of epigenetic reprogramming. Epigenetics refers to modifications in gene expression that occur over time, often due to environmental influences such as diet, stress, and exposure to toxins. Over the years, harmful epigenetic changes accumulate, leading to cellular dysfunction and the decline of vital physiological systems. By using specific interventions, such as lifestyle modifications, pharmacological agents, or gene therapies, scientists aim to reset the epigenome to a more youthful state, effectively reversing aspects of aging at the cellular level. Research into longevity pathways has identified several molecular targets that play a critical role in aging and its reversal. Among these are sirtuins, a family of proteins that regulate cellular repair and energy metabolism. Sirtuins are activated by calorie restriction, fasting, and compounds like resveratrol and nicotinamide riboside (NR), which have shown potential in extending lifespan. AMPK, AMP-activated protein kinase, a cellular energy sensor that is activated by exercise, fasting, and drugs like metformin. AMPK enhances mitochondrial function and reduces oxidative stress, two key factors in slowing the aging process. mTOR, mechanistic target of rapamycin, a pathway that regulates cell growth and metabolism. Suppressing mTOR through interventions like rapamycin, intermittent fasting, or ketogenic diets has been associated with increased lifespan in animal studies. Senolytics, compounds designed to eliminate senescent cells, which accumulate with age and contribute to chronic inflammation. Removing these aged cells has shown promise in improving tissue function and extending lifespan in preclinical studies. NAD+ restoration, nicotinamide adenine dinucleotide (NAD+) is a critical molecule involved in cellular energy production. NAD+ levels decline with age, but supplementation with precursors such as NMN, nicotinamide mononucleotide, has been shown to restore mitochondrial function and potentially slow aging. These interventions are not only being tested in laboratory settings but are increasingly being adopted by biohackers, longevity enthusiasts, and entrepreneurs like Bryan Johnson, who are self-experimenting with personalized protocols aimed at reversing biological age. While early results are promising, the long-term effects of these interventions remain uncertain. Large-scale clinical trials are needed to determine whether these strategies can deliver sustainable age reversal benefits without unintended consequences. Beyond the biological mechanisms, one of the most significant barriers to widespread adoption of longevity interventions is accessibility. Currently, advanced age reversal protocols involve extensive biomarker testing, personalized supplementation, and highly regimented lifestyle modifications, all of which require significant financial investment. Bryan Johnson, for example, reportedly spends millions of dollars annually on his Blueprint longevity program, which includes round-the-clock biomonitoring, specialized treatments, and a meticulously controlled diet. While such an approach may be feasible for high-net-worth individuals, it is impractical for the average person. The challenge for longevity science is to develop scalable, cost-effective solutions that can benefit a broader population. One potential solution is the integration of artificial intelligence and data analytics into longevity medicine. AI-driven health optimization platforms are already being developed to track biomarkers, predict disease risk, and generate personalized health recommendations. By using continuous health monitoring devices, such as wearable fitness trackers, glucose monitors, and sleep sensors, individuals can gain real-time insights into their biological aging process and adjust their lifestyle accordingly. This form of precision medicine could make longevity interventions more accessible by providing evidence-based, data-driven guidance without the need for expensive medical consultations. Another major area of longevity research is regenerative medicine, which focuses on repairing and rejuvenating aging tissues. Stem cell therapy, gene editing, and organ regeneration are among the most promising strategies in this field. Scientists are working on techniques to rejuvenate aged cells, replace damaged tissues, and even grow functional organs in laboratories. If successful, these advancements could drastically reduce age-related diseases and extend health span by addressing the root causes of cellular aging. However, the potential of extreme longevity interventions also raises profound ethical and societal questions. If humans begin living significantly longer, how will that affect population growth, resource distribution, and societal structures? The traditional life trajectory, education, career, retirement, may no longer be relevant if individuals remain productive for 100 years or more. This shift could necessitate new economic policies, workforce restructuring, and adjustments to pension systems to accommodate an aging but active population. Furthermore, the psychological and philosophical implications of extended lifespans must be considered. Historically, the human experience has been shaped by the inevitability of mortality. The knowledge that life is finite has driven individuals to seek meaning, purpose, and fulfillment within a limited time frame. If aging becomes largely preventable, will people still feel the same sense of urgency to achieve their goals? Will extended lifespans lead to greater happiness and fulfillment, or could they result in existential stagnation? These questions are central to the ongoing debate about the future of longevity science. Critics also warn of potential risks associated with extreme longevity interventions. While reversing biological markers of aging may improve short-term health outcomes, the long-term effects remain unknown. Some researchers caution that manipulating fundamental biological processes could lead to unintended consequences, such as increased cancer risk, immune system imbalances, or metabolic disorders. Additionally, concerns about genetic engineering and biohacking raise questions about the ethical limits of human enhancement. Where should the line be drawn between medical treatment and the pursuit of superhuman longevity? Despite these challenges, interest in longevity science continues to grow. Governments, biotech companies, and private investors are pouring billions of dollars into aging research, with hopes of making significant breakthroughs in the coming decades. The rise of longevity-focused startups and research institutions signals that the field is entering a new phase of rapid development, where scientific advancements may soon transition from experimental treatments to mainstream healthcare solutions. In conclusion, the case of the man who reversed 10 years of biological aging through Bryan Johnson's protocol represents just the beginning of a larger movement in longevity science. While his results demonstrate what is possible with rigorous interventions, the broader question remains: can these strategies be refined, scaled, and made accessible to a larger population? As research progresses, the future of aging may shift from an inevitable decline to a condition that can be managed, delayed, or even reversed. However, alongside these scientific advancements, society must prepare for the profound economic, ethical, and philosophical changes that may come with the ability to significantly extend human lifespan. The pursuit of longevity is no longer just a personal endeavor, it is a societal transformation that will redefine the way we think about health, aging, and the very nature of life itself.